We're now going to spend some time talking about a digital signal and an analog signal. We have electronic components that we will be testing that provide a digital signal and an analog signal. The signal that you can see on the left side is a digital signal, and the signal on the right is an example of an analog signal. A digital signal only has two states. Those states are either off or on. They could also be represented electrically. The off state could be 0 volts and the on state 3.3 volts. The two states of 3.3 volts and 0 volts are the only states that a digital signal can be set to. There is no in-between state that would represent 1.5 volts. Now when we look at the analog signal, we can see that an analog signal has an infinite number of states, or a continuous amount of states. It is not just simply on or off. An analog signal can be at 0 volts, 1.5 volts, 3.3 volts, and many other voltage ranges as it moves up and down the sine wave. Let's take a look at both the digital signal and the analog signal next to each other and identify the properties that we have just talked about. A digital signal has an on or off value. Those on or off values are represented by a voltage number. In the example, I put 0 as off and 3.3 as on, but that voltage range could change. The only thing to take into consideration is that it is either on or off. There is not a middle voltage that can be represented as a state in a digital signal. In an analog signal, we have a number of different states that the signal can be in over time. The analog signal can represent 0 volts, 1.5 volts, 3.3 volts, and so on. Like the digital signal, it also could go up to a larger number. You may be up to 12 volts, 120 volts, and so on. It's important to understand the difference between these two types of signals. Some systems and components do better when they're using an analog signal. Others work better with a digital signal. There's a couple things that we would take into consideration when determining whether or not to use an electronic component with a digital signal or an analog signal. When precision is important and calculations need to be exact, a digital signal does a better job. If there's any varying in voltage from the source voltage on the board, there may be changes to the analog signal. There would also be changes to the digital signal, but with ranges, you would be able to still determine whether it was an on or an off state. So for example, in a digital signal, if my voltage, source voltage, were to drop to 2.5 volts, I could not get to that 3.3 volts that would indicate an on state. In order to compensate for that, the program would look for a range. So anything between 1.5 and 3.3 volts would be considered an on state. Anything below that would be considered an off state. So we would still be able to get the precision that we need, and we wouldn't lose the on and off state benefits of a digital signal. An analog signal could have problems with evaluating the information it's receiving from the sensor if the voltage is varying. Having the voltage decrease to a 2.5 volts as the peak may cause problems when we're trying to analyze this signal that we're receiving from the electronic component. Another reason to use a digital signal over an analog signal is that our electronic component is connected to a computer. A computer communicates in binary. Binary is a two-state system. The computer communicates in zeros and ones. 0 is an off state and 1 is an on state. An analog signal has to be converted in order for the computer to understand the signal coming to it. We will be using both digital and analog electronic components in upcoming lessons. We'll look at the way that each of these electronic components communicates with the CPU and some of the advantages and disadvantages of using each type. The last item that I would like you to do is navigate to this URL. The article discusses both analog and digital signals and may help clear up anything that you don't understand so far. I wanted to point out a few things in the article. Hopefully you've taken the time to review this yourself. When we're talking about analog signals, we can think of a clock as an analog signal. This is an analog voltage that is taken. Down here we have digital signals. They can only be represented in a state. So that's a very important distinction that we find. Here is the analog signal. We'll look at this as the 120 volt AC signal that we would see coming through our at our houses. So it goes up to 120 and then down to 120. It's actually alternating the current. An analog signal can also be part of a DC circuit, so don't get those confused. AC and DC doesn't necessarily distinguish. DC is direct current and AC is alternating current. Analog signals can be DC. Here's an example of an analog signal that things are changing over time. So when we look at these graphs, you can see it pointed out right here. Time is what is changing. So the voltage value is changing over time. Here we have a certain quantity of time has passed, and then we see these changes in the signal. So it doesn't necessarily have to be an analog signal. It might be have kind of these sharp edges to indicate a certain range or specific value. All right, this section of the article talks about digital signals. We talked almost exclusively, well, exclusively in the video, we talked about this portion. So we have an on and an off state. This is a two-value square wave signal. Here's the square waves as it goes on. Here it's off, here it's on, here it's off. You can have more than one state or more than two states. So almost everything that we deal with will be this. And the reason that it's this is because it's communicating directly with a CPU who communicates in 0 and 1s. The other option is to simulate a stepped sine wave. So you can see that this isn't completely smooth. However, we do see that it steps up. So we are having multiple states in this type of a scenario. However, almost all of our electronic components are going to be communicating in this two-state value. That's the most common way for us to be able to communicate when a computer is involved. But keep in mind that we can almost replicate a sine wave. However, notice that it's not smooth, so there is a finite amount of values. Whereas an analog signal that has a sine wave, this is an infinite number of values.